So now we're going to learn how to quantify charge and electric forces through what is called Coulomb's law. We all know that electric charges can exert forces on things. After all, if you take clothes out of the dryer that are full of static electricity, they make the hairs on your arm stand up. We can feel the forces due to static electricity, which is really nothing more than excess charges on objects. Coulomb's law gives us a way to measure those forces. By the end of this video and the optional video on additional examples of Coulomb's law, you should be able to calculate the magnitude and direction of a force on a positive or negative charge due to other specified point charges and analyze the motion of a particle of specified charge and mass under the influence of an electrostatic force. In this video, we'll start by looking at charges, atoms, and molecules, and then introducing Coulomb's law. We will then move into seeing a few examples of increasing complexity and also compare the strength of the electrostatic force with the strength of the gravitational force. So, off we go. So we've been talking about charges, and we've briefly alluded to what they are, but we need to spend a little bit of time explaining them a little more fully. Charge, like mass, is an inherent property of protons and electrons. There are no other sources of charge other than protons and electrons. An object is charged if it has an unequal number of protons and electrons. If something has excess electrons, it has a negative charge. If it has excess protons, it has a positive charge. If it has an equal number of protons and electrons, it has a neutral charge. So now the process of removing an electron from an atom is called ionization. The resulting atom is then called an ion. Positive ions are called cations, negative ions are called anions. The charging processes that we've explored so far involve rubbing and friction. The forces of friction often cause molecular bonds at the surface to break as two materials slide past each other. Molecules are electrically neutral, but molecular ions can be created when one of the bonds in a large molecule is broken. If the positive molecular ions remain on one material and the negative ions on the other, one of the objects being rubbed ends up with a net positive charge and the other with a net negative charge. This is the way in which a plastic rod is charged by rubbing with wool, or a comb is charged by passing through your hair. The breaking of such bonds is also responsible for the charge on Scotch tape that's pulled from the roll. Now, in chemistry, you probably learned that a proton has a +1 charge and an electron has a -1 charge. Chemistry really loves that, but this plus and minus one business doesn't work very well when we go in and try to do the major figuring out stuff. It's kind of an arbitrary thing, so we need a really useful unit of charge. Well, we happen to have one, and it's called a Coulomb, abbreviated by a capital letter C. Now, 1 Coulomb is equal to the amount of charge on 6.25 times 10 to the 18 protons or electrons. So this number of protons and electrons, the charge on that number of electrons and protons equals 1 Coulomb. Well, how much charge then is on 1 proton or 1 electron? The charge on a single proton or a single electron is 1.6 times 10 to the -19 coulombs. It's a positive, it's a positive 1.6 times 10 to the -19 coulombs if it's a proton. If it's an electron, it's negative. So we have this 1.6 times 10 to the -19 coulombs per electron. So let's say we have something like 1.35 times 10 to the 17 electrons. And we want to know how much charge that is. We multiply that by the 1.6 times 10 to the -19 coulombs per electron, and we end up with 0.0216 coulombs. Now, one last thing before we move on. The symbol that we use for charge is a Q. In physics, the term quantity of electricity refers to the quantity of electric charge. So it's designated by the letter Q, and in the SI system is measured in coulombs. Okay, so Coulomb's law tells us about the strength and direction of the force that charged objects exert on one another. The electric force is a field force. It's a force exerted by a field around charges. This is very similar to what happens with gravity between two objects that have mass. Hopefully, you remember Newton's universal law of gravity can be used to calculate the force between two objects that have mass. Well, it turns out that there's a similar law that can be used to calculate the force between two objects that have charge. This is called Coulomb's law. Coulomb's law can be stated in two parts. The first part will tell us about the magnitude of the force, the second, its direction. Coulomb's law states that if two charged particles having charges Q1 and Q2 are distance r apart, the particles exert a force on each other of a magnitude that's proportional to the product of the charges and inversely proportional to the square of the distance between them. So this gives us Coulomb's law equation, where the force between charges is equal to a K, a constant, that's called Coulomb's constant. The value for Coulomb's constant is 9 times 10 to the 9 Newton meters squared over Coulomb squared. We've got Q1 and Q2, those are the two charges that are next to each other, and the distance between them. Now, the force between two charged objects can be either attractive or repulsive depending on whether the charges are like or unlike. We're also assume that the charges are concentrated into a small area, so they're point charges. Also, it's important to remember that the electrostatic force between point charges is a force. Newton's laws apply to this force. Therefore, a net force can make a particle accelerate, and the force between two different charges is equal and opposite. So definitely keep that in mind and make a note of it. Let's go ahead and take a look at an example. Here we have two 10 nanocoulomb charges 2 centimeters apart. We want to know the net force on a 1 nanocoulomb charge midway between them. Now, because 1 coulomb is a pretty large amount of charge, it's really common to use microcoulombs or millicoulombs, or in this case, nanocoulombs. Nano simply means times 10 to the negative 9. So all we have to do with these is take the 10 and times 10 to the negative 9. And so what we're trying to figure out is what is the net force on this charge in the middle between two positive 10 nanocoulomb charges. Well, the force on this particle due to the one on the left is going to be directed to the right. They're like charges, so this charge will repel this charge. Well, over here, this charge will also repel this charge, and because they are of equal magnitude, the two charges on the ends are of equal magnitude, then we end up with a net force of 0 newtons on that middle particle. Okay, but what happens if we replace that right-hand particle with a negative 10 nanocoulomb charge? In this case, what's going to happen is the one on the left will push it to the right, will push the middle charge to the right, and because of opposite charges, the one on the right will pull the middle one to the right, and we're going to end up with a net force to the right. So Coulomb's law will tell us the magnitude of that net force. What we do is figure out one of those net forces and then simply double it. So when we throw in Coulomb's law and put in our values, this is what we end up with. Now we could use either the positive charge or the negative charge to figure out the force. If we use the positive charge, we got our positive charge here. We could use that negative charge, and if there was a negative here, our answer would end up being in a negative, but all that really would tell us is that it is a pulling charge. Okay, so that negative would only indicate direction. So we work this out and we make sure that we have our distance is midway between the two larger charges, so it's 0.01 squared. So we end up with 9 times 10 to the negative 4 newtons. Well, that's the force for one charge, so we double that and we end up with 0.0018 newtons as our net force. So both gravity and the electromagnetic force are two of the 4 fundamental forces of nature. The other two are the strong nuclear force and weak nuclear force. So what we're going to do right now is going to undertake a comparison of this electromagnetic force and gravitational force. To do that, we're going to compare the forces in a hydrogen atom. So the hydrogen atom is made up of a proton and an electron. The two particles attract each other because they both have mass, so they attract each other by gravitational force, but they also have opposite charge, so they repel each other due to the electromagnetic force. The charge on each is this 1.6 times 10 to the negative 19 coulombs. The distance between them is 5.3 times 10 to the negative 11 meters. The mass of an electron is 9.1 times 10 to the negative 31 kilograms, and the mass of a proton is 1.7 times 10 to the negative 27 kilograms. So let's start by calculating the force of gravity between them. So when we apply Newton's universal law of gravitation to the force of gravity between a proton and an electron, we end up with this 3.67 times 10 to the negative 47 newtons. Well, that there is not a lot of force. So let's take a look at the electric force. Coulomb's law shows us that the electric force between a proton and an electron in a hydrogen atom is 8.2 times 10 to the negative 8 newtons. Now, taken on its own, that's not a lot of force itself, but when compared with the force of gravity between the two, we see that that electric force is some 2.2 times 10 to the 39 times larger. It's a much, much larger force than the force of gravity. When you think about it, that makes total sense, right? Because you can take a balloon and drop it to the ground and it falls. Gravity pulls it down. But you can take that same balloon and put just a little bit of charge on it and stick it to a wall. Just doing that is counteracting the force of gravity. So we can defy gravity way easier than we can defy the electrostatic force. So when we go to compare the electrostatic force and the gravitational force, we really find four significant differences between the two. Gravity is always attractive. The electromagnetic force can be either attractive or repulsive. Gravity is much, much weaker. Gravity has a much greater range in which it is a significant force, and the electric force can be shielded, blocked, or canceled. You can't do that with the gravitational force. And finally, the gravitational force is around 10 to the 40 times smaller than the electromagnetic force, which can be seen in the comparison of those two proportionality constants. So really, the last thing to kind of deal with before ending is we need to talk about the superposition principle, which we saw in the first example that we looked at here in this video. When we have more than two charges in proximity, the forces between them get a little bit more complicated, but just even though they seem complicated, they really aren't. It's fairly simple to work things out. The forces, being vectors, just have to be added up. We call that the superposition principle, which states that the resultant force on a charge is the vector sum of the forces exerted on it by other charges. I'm going to look at that a little bit more in depth in the optional video dealing with just a few examples. I'll throw a few examples on there, and we're going to take a look at the superposition principle. So make sure you check that out.